Okay, so the problem we'll be working on is figuring out the geometric properties of this cross-section. We've got in what is obviously an I-beam here. So its depth is 150 millimeters, its width is 100 millimeters, and the thickness of the web is 4.32 millimeters. Thickness of the flanges is 5.5. Flanges, web, flange. So first off, cross-sectional area is fairly simple. So again, we can just find the area of a big box like this, and then we can subtract the area of these sections that aren't included. So that's simple enough. So 150 millimeters times 100 millimeters, and then the total area of this section, that's just going to be equal to the 100 millimeters minus the width of our web here, times the 150 millimeters minus 2 times the thickness of our flanges, because there's 2 of them. And that works out to 1700.5 millimeters squared. Location, we're just going to base this upon our axis of symmetry. So we got one axis of symmetry that goes right here. Well, still can't draw a straight line on this tablet. Right here. And we got another one that goes right there. So we know that the axis of symmetry is located in the center. Relative to this bottom corner here, it's 50 millimeters this way and 75 millimeters up. Next thing we're going to want to do is calculate our IX. For this one, we'll use the method of adding the sections together. So we know that for a box, IX is the base of the box times the height of the box cubed, all divided by 12. I didn't want to do that. I want to do that. So basically what we need to do is we need to kind of break it up into components and add the contributions from those components together. So I broke it up into A, B, and C. A is going to be our top flange, C is our bottom flange, B is the web in the middle. So figuring out the individual components of that, again, we're going to need to use our parallel axis theorem. So we got the I of the box if it was taken from the origin at the centroid of that box, and then just plus the area of the box times the y distance squared. So for here, we're going from the centroid to the centroid of the top flange. So that'll be the 150 divided by 2, so 75. 75 is the distance from here to the top edge here, then minus half the thickness of the flange. So that'll work out to 72.25 millimeters for our dya. Our area of A, it's simpler to do. It's 100 millimeters wide. It is 5.5 millimeters thick. So we get our 550 millimeters squared. And then we just use this formula here for our Ix prime A. So base times height cubed divided by 12, 100 times 5.5 cubed divided by 12. That works out to 1,386.5 millimeters cubed. Nope, not cubed to the 4th. I really got to stop doing that. So we need to go ahead and add all that up. So again, we've got our are 1,386 millimeters to the fourth, and then we multiply that by the y distance that we calculated here squared times our area, 550 millimeters squared. I realized that I had put this squared in the wrong spot here. My apologies, but when I punched it in the calculator, it did do it correctly. So this value here that we get is correct. So we got basically 2.87 times 10 to the 6 millimeters to the fourth. So, relatively large number compared to the IX prime A, and that really shouldn't be too surprising. The fact of the matter is that if we just had a bar here, and we were trying to bend that bar, it wouldn't resist it all that much if we were just bending it about its centroid. The entire purpose of having the flanges on an I-beam is so that they are separated vertically, so that they have a much larger contribution to its IX than it would otherwise. So if we wanted to just have a thick bar that had an IX that was similar, then we'd basically have to use up a lot more material before we got to something equivalent. So that's why I-beams exist, because they're able to resist bending a lot more because of that vertical separation of the relatively thin flanges. So that's the IXA there. So obviously we've got our IXA. We also need to know what our IXC is for the bottom flange, but thankfully we know that that is going to be equal to the IXA because, again, the dy term is squared. So the fact that the displacement from the centroid of the thing to the centroid of the bottom flange is negative doesn't matter. That, the negative sign cancels out. Everything else is identical. So it has the exact same contribution to the IX overall as the top flange does, which isn't surprising at all. It's symmetrical. That's what we kind of expect. And then we got the contribution from the IXB. So in this instance, there's, the centroid of the web is at the centroid of the overall structure. So our ADY squared term is 0 because our dy is 0. So the only contribution we get is from the IX prime B, which again is going to be larger than the IX prime that we saw from A or C, just because we're cubing the larger number instead of the smaller number. So when we throw in, we got our base times our height cubed divided by 12, so that'll be 223,802 millimeters cubed. Not like we really care about the 802. So that's the contribution from the B, which is basically completely overpowered by the contribution from the X and the C. So adding those two together, the IX is going to be equal to 5.97 times 10 to the 6 millimeters to the fourth. So that, essentially there is certainly some contribution from the IXB, but it's relatively small. If we neglected it, we'd be looking at 5.7 instead of 5.9. So when you're designing an I-beam, you're designing the flanges in order to hold withstrain your bending. You're not relying upon the web to do that at all. The point of the web isn't for the bending resistance. The point of the web there is to hold the shear load, which we'll talk about later in the course. So let's go for our IY. Let's use the subtractive method here instead. So we can basically find the IY by finding the IY for the entire cross section. Just, our 100 millimeters and our 150 millimeters. If we had a solid steel cube or solid steel rectangle that with a cross section like that, and then subtract the contributions from these two shaded sections. So again, we still need to use the parallel axis theorem for those. So for IY, again, we're looking. It's similar to the X calculation, except we're cubing the base instead of the height here. So that's and then divide by 12 again. So for the so in this instance, A, I'm kind of talking the overall box, and then B and C are these shaded sections that we're removing here. So again, we still use the parallel axis theorem here, but in this instance, since it's co-located at the centroid, then our dx squared term 0. So we're left with just the dy prime for A. So our 100 millimeters is the base. Cube that times our 150 millimeters divided by 12. And then that gives us this value here, 12.5 times 10 to the 6 millimeters to the fourth. So now we just need to figure out what the IYB portion is. So again, we just we're working off the parallel axis theorem. So we find out what our area is and our displacement in the x direction to get the centroid. So again, we're going from here to there. So the area, so basically from here to here is 50, and we're going to shave off this tiny section here that's half the width of the web. So 50 minus 4.32 divided by 2, and then multiply that by this height here, which is 50 minus that 11 millimeters, which is twice the twice the thickness of the flanges. So that's 139 millimeters. So that, oh, I already had that written right there. Anyhow, so those two multiplied together, we get 6,650 millimeters squared. So our dx isn't too difficult to find here. We've got the thickness of our shaded section here, and we're halfway through that. And then we also have the halfway through the thickness of the web as well. So an additional, so got our 47.84 millimeters divided by 2 plus the 4.32 millimeters divided by 2. That gives us a dx of 26.08 millimeters. Our IY prime here, and I realized I mixed, it started on the previous page with B, I moved to C, I put C down here. Again, my bad. I should keep consistent. That having been said, we are in the same scenario here where the IY negative contribution from removing B and negative contribution from removing C is going to be the same thing because it's symmetrical. So again, just our base times our height. So this time we are cubing the base instead of the height, and then I'll divide it by 12. So that gives us the 1.27 times 10 to the 6 millimeters to the fourth. So our total IYC is just going to be that, plus invoking our parallel axis theorem. Got the area that we calculated, and we need the distance, the dx squared. So all those together works out to, oh, I didn't want to move that, works out to be 5.79, and again times 10 to the 6 millimeters to the fourth. So next thing that we know, our IYB is equal to IYC, again because it is symmetrical about the y-axis. So the IY total is just going to be the big IY that we initially calculated based upon the 100 millimeter by 150 millimeter block minus the contributions from these two sections. So that's 12.5 times 10 to the 6 millimeters to the fourth minus 2 times 5.791 times 10 to the 6 millimeters to the fourth, which gives us this value here, 0.917 times 10 to the 6 millimeters to the fourth. So compare that to our IX, and we see that it is significantly smaller, which really shouldn't be surprising. The entire point of having an I-beam is to resist bending about the x-axis. It is not designed, is certainly not optimized for bending about the y-axis. If you want something that's good at both, don't use an I-beam. What you want to be using is probably a square, some sort of square tubing. The next thing that we need to calculate to get the last of our geometric properties here is our IXY, but we know that's 0 by inspection because at least one of the x or y axes is an axis of symmetry. Is an axis of symmetry. So we can look at that and just declare IXY to be equal to 0. So that gives us the last thing that we're looking for. So if you're wondering why I kind of picked those values to work with, well, it was a convenient shape for one of the I-beams that you can find in the back of your book. So that's this one right here. So some slight differences between what we calculated and what they calculated. What we calculated and what they have. And again, that's kind of due to the fact that you got this curved section in here, whereas we had just squared. So you're going to have a little bit of influence there. So I think we had 1700 for the 1700 millimeters squared for the area. The I that we calculated, they've got 6.84 times 10 to the 6 millimeters squared. We had what did we have there? Yeah, so we had slightly less than that. Same idea for the I is on the same order as well. So slight differences, but looks like it's roughly matching. So yeah, and that's how you do those ones.